All right. Geodesy, time for more. So, as we are wrapping up our development of the sphere as a model of the Earth, and before we move into the ellipsoid, I wanted to expand on our spherical model to start developing or just briefly develop the idea of the celestial sphere. The celestial sphere is used in astronomy, it's used in satellite mathematics. What else? Yeah, any type of navigation using the sun or the stars. We develop our solar azimuth by using the celestial sphere. So what the celestial sphere is I'll just write it up here. The celestial sphere. So we have this. We already have this mathematical model of the Earth. That's a sphere, and we said that, and this is the lateral view, by the way, the front view. Here's the equator and the pole. And we said that our system of axes, whether it be our Earth-centered, Earth-fixed, or our graticule, is centered at the center of mass of the Earth. Well, what if we were to expand that sphere so that it's still centered on the center of the Earth, but the Earth itself is infinitesimally small in relationship to the celestial sphere. So we're expanding the sphere out to a radius that approaches infinity. So the celestial sphere, the radius, I hate writing with red, so the radius tends to infinity. So we're not fixing a radius in order to use the sphere, and it makes sense because in everything we've done, every calculation we've made, it doesn't matter if our point is on the surface of the sphere, below the surface of the sphere, or above the surface of the sphere, right? We're only concerned with the distance from the center of the Earth. Well, we can sure use the same concept. Those dots are supposed to be on that line, but we can use the same concept and not worry about the surface of a sphere. So the celestial sphere is an abstract concept. It's an imaginary sphere with a radius. You'll hear people say that the radius equals infinity, which doesn't make sense because infinity is not a number or a quantity. It's just a concept. But we can say that the radius tends to infinity, much like in calculus we do a lot of analysis where we look at what happens when we let a certain value, say x, approach infinity. So the celestial sphere, infinite, or radius that tends toward infinity, and so how do we use that? I'm just going to erase what I've drawn so far. We'll get back to it. So now, instead of the pole and the equator, we have the zenith and the equatorial plane, the celestial equatorial plane. And if I were to draw the Earth, not to scale, but if I were to just draw the Earth here-ish, then the spin axis, it's not quite centered, but the spin axis of the Earth is here. And I'm going to use a different color. I'll use red. So here's the spin axis of the Earth. Here's the equatorial plane of the Earth. And all we're doing to get the axes we need for a coordinate system on the celestial sphere is just expanding those all the way up. So we're just expanding our spin axis up to the zenith and down as well. And then we're expanding our equatorial plane out to infinity, or tending to infinity, or approaching infinity. So with that, we can talk about a quote-unquote latitude and longitude the same way. However, in a celestial sphere environment, of course, we have to use different terminology, right? It seems like terminology changes with each application. But really, we're going to find that those are the same as latitude, longitude, height, radius, and so on. And you can probably guess that, let's see, let me get my other view here. And I'm going to just bigify it so it's easier to imagine as a gigantic sphere. So this would be the top view of the celestial sphere. And much like in the last image, we expanded the spin axis and therefore the z-axis of our Earth-centered, Earth-fixed system. Well, we can do the same here. This would be if the Earth were here in the center. If the Earth were here in the center, and the Earth has the x-y axis looking down. Remember, we're looking down at the equatorial plane or at the pole. Then we're just expanding the x and y axis out. And so we have the same coordinate system, right? And of course, the latitudes and longitudes would become the celestial graticule system, although we're not calling them latitudes and longitudes. We'll get to that. So let me bring back the other image. So here is our lateral view of the celestial sphere. And I'm going to erase all my stuff. I'm working with images. It's easier just to erase the stuff that's there rather than try to recreate the image. Okay, so the celestial sphere, a couple of bullet points. I'll write them over here. It's centered on the gravitational center of the mass of the Earth. So same as our spherical model of the Earth, right? And as we stated before, these are just some bullet points about the celestial sphere. The radius tends to infinity. What else can we say? So just like our spherical model of the Earth rotates with the Earth, the celestial sphere rotates with the Earth. Okay? So the value is that we can actually take positions, celestial bodies, even our own position, and project them onto the surface of the sphere. So we can project celestial bodies that is the sun, stars, etc., onto the CS for celestial sphere with the appropriate radii. Radii being the distance of the particular celestial body from the center of the Earth. Okay? Not that, after everything we've looked at with the spherical Earth model, it's not that complex. We're just using a more convenient model to so that we can account for the positions of stellar bodies or celestial bodies in a reliable way and perform the mathematics thereof, right? So again, let's say we have an Earth here. Not to scale, of course. And let's say here's my position on the Earth. And let's say we have a star, well, up in here. And they are, positions that are obviously less than infinite radius. But we can, in order to do the mathematics, we can project, I'll use that color. No, I'll use this color. Project my position. So this is my position, me, right here. This is some star. And then we project that position up to the celestial sphere. And the same with the star. I'm not going to put it there. It's going to make it tough to draw. Let's say it's here. So project it up to the face of the sphere, and the star, same thing. I can project it up to, say, I don't want to put it there. It'd be hard to draw here. So here's the star I'm looking at, and here's the star on the surface of the celestial sphere. So this would be, we tend to call this Z. Z, and Z is my position projected onto the celestial sphere, and S, here's the star down here. I'll put little bullet points here. S is the, I'll just say star, but really any celestial body. Star's position projected onto the CS. Okay? Now we can start using the same geometries we used before. So we have the great circle arc between Z and S, and we would have the complement of some latitude from Z to the zenith. This is the zenith. We no longer have a pole. And the same with this. So we have a spherical triangle, don't we? And we can perform all the mathematics the same way. So if we were on the spherical model of the Earth, we would call this angle what? What would we call that angle? Remember, we're looking, this is a lateral view. Well, we would call that psi on the Earth model for latitude. However, on the celestial sphere, we actually call it this small letter delta for declination. Put equals declination. So another bullet point over here, declination is analogous to latitude, right? And this, I'm not going to pull over the other image and do a top view because we know what longitude is. This line, so that's the declination of S. And likewise, I would have a declination of Z, right? The declination, my little D. That's the declination of Z, or our projection, the projection of me onto the celestial sphere, just like latitude. Well, we also have, what color should I use now? How about pink? An equivalent for the longitude, right? So Z lies on this line of longitude, but instead of longitude, so on the spherical model of the Earth, that would be lambda, but we don't use the same terminology, do we? This is called the Greenwich hour angle, or GHA. And I'll put a bullet point over here. GHA is, I'm running out of room, aren't I? Oh, 2 E's. Greenwich hour angle. And it's analogous to longitude. Pretty familiar stuff. And just like on the other model, this would be our declination complement up here. So this is 90 degrees minus the declination of S. Okay, what did I miss? Then we can also compute azimuths the same way, can't we? And just like on the Earth model, this angle would be our azimuth. And we still call it azimuth. Okay, that would be the azimuth from Z, from my projected position to the star's projected position. Okay, and then the spherical laws that, or formula that we've been looking at would apply the same way, right? Easy stuff. So just an interesting little side note. So zenith, we have Polaris up here, right? I guess it would be, here's Polaris. Which is really, really close to being on that zenith line, that extension of the spin axis of the Earth. So that's Polaris, which is why we call it the North Star. It actually does move a tiny bit with the tilt axis of the Earth. From our perspective, it does make a little teeny tiny circle around the zenith line. But it's close enough that we can, if we need more accuracy, we can mathematically account for that difference from the zenith angle. But in most cases where we're incorporating a celestial sphere, it suffices just to consider Polaris as being on the zenith line. Okay, and I'll erase a bunch of this stuff so I can write more. can always go back, and if you didn't get it all copied down, that's the beauty of recorded lectures, is pausing or rewinding so we can get all this right. Just a little bit of terminology. If let's see, so this red dot being me, this line that runs from the center of the earth through me and to my projection up here on the sphere is, there's a downward from myself and an upward from myself. So if this is me on the earth, I have an upward direction, right? Straight from the center of the earth. And I have a downward direction, which goes to the center of the earth, center of mass, the earth, right? The upward direction we call zenith, and we've all heard that before, the zenith angle. We have a choice when we get a vertical angle. We could get either the vertical angle from the horizon or from the zenith down to us. So that's where zenith angle comes from, that's what a zenith is. The downward direction has a different name. That's called a nadir. So the nadir stretches from the center of the earth to me, and then the zenith is the projection of the nadir through me up to the celestial sphere. So on the diagram, this would be the zenith, my zenith. And that part would be the nadir. So just getting some terminology. Let me just scoot this over so I have more writing space. I'll leave that here. All right, so Greenwich hour angle. We talked about that just a second ago. It is the angular measurement of a celestial objects possessive of a celestial object's position let's see, relative to the Greenwich meridian or prime meridian. Just like on the Earth model. Okay, and like we said, it's analogous to longitude, and it looks just like the representation is just like longitude. It'd be degrees, minutes, seconds. And then we have declination, just defining terms here, which we denote by a little d, little Greek d, and that's the angle or the angular measurement use consistent wording here. The angular measurement of a celestial object's position relative to the celestial equatorial plane. Celestial which is there on the drawing. Celestial equatorial plane, CEP. Okay, and as we stated before, it's analogous to latitude, right? Cool. Moving right along. And I'm going to scoot this up before I get rid of it, because I have learned that my little picture-in-picture, I tend to write in space that I cover that up. I need to put a little rectangle down here or something so I don't write in that. So it is interesting to note, and I'm not going to show this pictorially, but it's pretty interesting how the geometry works using parallel lines and all that. So it is interesting to note. And this can actually be proven with a picture, that the position of Polaris, or the North Star, relative to the horizon which is the horizon is basically, if I'm on a sphere, it would be a line perpendicular to the nadir or the zenith where I am. So we haven't talked about that direction yet, but it's the same horizon that was used in plane surveying. Relative to the horizon, gives the latitude is equal to the latitude of the observer. So it's easy to find, right? Latitude is easy. With a sextant on a ship, the navigator or the captain would take a measurement on the horizon, and then would raise it up to Polaris, and whatever that angle is, that would be equal to the latitude of the observer's position or the ship's position. I think that's pretty cool. That's some pretty cool mathematics. So this concept is heavily relied upon, particularly historically, for navigation. It's helpful to know your position on the Earth, so that's how they got the latitude. Longitude is a different story, and we will talk about longitude as well. Okay, so in order to find one's position on the Earth, we use the aforementioned concept to get the latitude. Longitude is another story. So longitude is another story. So longitude calculations are a function of time. And the first calculation is really easy. I'll just go ahead and do that. So the Earth rotates through 360 degrees in 24 hours. And we can use that to get the change in the longitude per hour. Solving for that, we get delta lambda equals, if I divide 360 by 24, 15 degrees per hour. So if I know what the position of the sun is at 0 hour in Greenwich, England, and I can note what time it is where I am based on the exact position of the sun, not time zones or anything like that. Obviously, the sun moves continuously, not discretely. So, changing my time by 1 hour with each time zone is impractical. So when we're talking about time in this sense, we're talking about where the sun is in Greenwich hour angle and declination, where I am, where Greenwich, England is. So that's what I mean when I'm talking about time. You can think of it as a continual progression of seconds, right? So if I know that the sun has a certain position, certain Greenwich hour angle, or I'll just say latitude and longitude, or at 0 hour in Greenwich, and I take my position and I can tell how far I am from, in terms of degrees, using this 15 degrees per hour from the zero line of longitude. So that's how that's done. It's obviously a little more complicated than that, but in a nutshell, that's really how it's done. I'll just to exemplify that, it might be helpful. I don't want to do that. Here's the Earth, and here's me, and here's Greenwich, England, me, and here's Greenwich. I know that I lie on some line of longitude, and Greenwich lies on zero longitude. If I can calculate for my existing moment, in an instantaneous moment, the sun's position in Greenwich, and then calculate where the sun's position where I am, then that 15 degrees per hour, that'll be a time difference, right? If I multiply time times 15 degrees, that's going to give me this delta lambda, and then I can get my longitude. So where do we get this information with regarding what time and where the sun is in position X time in Greenwich, England? We use an ephemeris, which is a chart, or star almanac. Essentially, they're the same. They're all the same thing, just different wording. Or solar almanac, and you can get ephemerides for the sun. You can get ephemerides for any. I don't think any star, but the main stars that are used in navigation. And that would be something like, for example, let's see. If I were to look up a date, say, I don't know, today, or beginning of the term, how about? September 5th-ish. So let's say I'm interested in performing a solar observation on September 5th, and I were to look that up in the ephemerides, then I would see that at 0 hour, I would have a specific Greenwich hour angle in Greenwich and a specific declination. So we'll call it GHA1, GHA2. And since the sun's position changes from our perspective with the time of year, the tilt axis of the sun as it orbits, and the Earth has an elliptical orbit around the sun, and it's similar to the stars at 24 hours. Then the sun will be close to the same position, but slightly different. So Greenwich hour angle 2 and declination 2. These would be, in the ephemeris, these would be actual angles. And let's say that I am taking my observation at noon. Or 9 o'clock, or let's say 9 a.m. Since I'm taking the observation at noon, I would need to interpolate. That falls between 0 and 24. I would need to interpolate the Greenwich hour angle and declination from what it would be at noon given the GHA1 and the GHA2, or the 0 hour and the 24 hour. Just a demonstration of interpolation. We're not going to go real heavy into, we're not going to go heavy at all. This is a conceptual lecture. We're just looking at the concepts of the celestial sphere, but how we would interpolate is, so let's see, need an example. Let me see if I have an example somewhere in here. Okay, so let's say that we look up our information here. So we look that up, and we see that at the 0 hour, we have a GHA, Greenwich hour angle, of 180 degrees, 30 minutes, and 0 seconds. And at the 24 hour, and this is a linear interpolation, so it's super easy. We don't have to account for any kind of logarithmic curve or something like that. At the 24 hour, we have a GHA of 181 degrees. Okay. So this is information from the ephemeris. Info. And we're just going to do the Greenwich hour angle. We would do the same thing for the declination. Info from ephemeris or almanac. All right, so we observe, we make our stellar observation or our solar observation, say at noon. Then all we would do, noon is 12 hours over 24 hours, and we would just multiply that by the change or the difference in the GHA. So that would be 30 minutes, right? The difference between this and this, that's the total difference, and we're going to look at the ratio, or we're going to apply the ratio of our noon observation to the change in the Greenwich hour angle. And then we would have to add that then to the 0 hour Greenwich angle, right? Which makes sense because we know that our number is going to be between here. It's going to be somewhere between 180 and 181. So we have to add that 180. And if we did that, we would get 1/2 times 30 seconds, so 0 degrees, or sorry, 30 minutes, 00 seconds. And then we would add it to 180 degrees. Oop, that should be 30 minutes up there. The 0 hour GHA is 180 degrees, 30 minutes. So 30 minutes, 00 seconds, and we get 180 degrees, 45 minutes, 00 seconds, which is the Greenwich hour angle of whatever we're observing. Let's say, I'll just say the celestial body that we're observing, whether it's a star or the sun, at noon. Scoot that up a bit. And I probably hid those last little bits, so I'll just leave those there. Couple of bullet points. We can interpolate the declination the same way. Right? Where am I in my notes? Okay. When we take an observation of the sun, so I'm not sure if you've done a solar observation yet or not. It's actually a different class, so we're just going to touch on the topic. We're not going to actually go through the calculations. But if you think about it, if the instrument's here, and I'm taking a solar observation up here, well, we take an observation. There's a couple ways we can take an observation. We can take an observation to the edge of the sun, so that would be a line tangent to the sun. And then account for the semi-diameter of the sun to get the angle we really want, which is here. So that first line, that's a measured angle, and this line is a calculated angle. And you'll also see where people sometimes will, and I should say the ephemeris also gives the semi-diameter of the sun on a specific date and time. So that's, if you look up a chart, it'll have the Greenwich hour angle, the declination, and the semi-diameter of the sun. So you can actually perform the calculation. And I haven't done this, but some people have said you could actually take that observation to this side of the sun and then wait for it to pass, and eventually it'll pass and it'll be here. So we would take the observation there and calculate the difference and or how much time it takes for the sun to move, and you can perform a calculation and get the semi-diameter of the sun right there, or you can just get it from the chart. So that would give us this little angle here. To correct, that's the diameter correction for the sun. Okay, just took a second to clean up my screen. So I can demonstrate this in a better way. Hopefully it's a better way. So let's say here's my instrument. I'm making it nice and big, little instrument symbol. So we know that it's really close. And then up here I have the sun, and back here I have my back sight. And the first observation I would make is that I would zero my back sight, right? Just like we always do. And then I would measure the angle tangent to the sun. The reason we don't measure directly to the center of the sun is because that's less accurate. We can't really eyeball the center of the sun as easily as we can eyeball the tangent. So we have these crosshairs, and here's the sun, and as it moves, I would catch it as it just touches the crosshairs and record that time and angle. Because we need both the time and the angle to perform these calculations, right? So once I have that, I would consult my ephemeris that I've already interpolated all the information, and I would apply the semi-diameter to calculate the angle to the center of the sun. And what that is so here is the, I were to draw a line that's perpendicular to my observation line, that distance is the semi-diameter of the sun, and that's what the ephemeris gives us. So that gives me, let's see, I'll use green. Now I have this angle, right? So I have a horizontal angle from my back sight to the center of the sun, the center of the sun's position on the celestial sphere. Then I would apply, the Greenwich hour angle and declination from the ephemeris. So if I move this up a little bit so I'm not losing my now apply the Greenwich hour angle and declination from ephemeris to calculate the azimuth to the center of the sun, COS, center of the sun. Okay. So since I have the azimuth to the center of the sun, I can calculate where true north would be, or solar north. So now I have north. Let's say that's north. Now what I have is this angle, and I can then subtract my horizontal angle. So if this is my horizontal angle, this is my sun azimuth, I'll say AZ sub S. Then I can subtract my horizontal angle minus the azimuth of the sun, which gives me, well, I guess it's not as simple as subtraction. I have to add 360 to that because the azimuth, remember, is defined as being in the angle in relationship to north in a clockwise direction. So now I have that angle. And that angle is my azimuth of back sight. So my as sub BS. And that's what I'm really wanting. Now I have the azimuth of my back sight in relationship to solar north. These are reproducible results that I can publish with my survey so somebody else can come along. They can calculate the same north and get the same azimuth within 20 seconds. So there's 20-second fudge in the process of getting solar north. So that's how we do that. Once we have the azimuth of our back sight, we can get the azimuth of all our other observations in the network, right? Cool. And since it's important, I'm just going to say this is our measured horizontal angle, and this green line is our calculated horizontal angle. Okay. And that's how we do a solar observation. There's some spicier equations involved in formulae involved in that. If you've already done a solar observation, then you know, hopefully you did it by hand. You've had the chance to perform a solar observation by hand and run through the calculations rather than just using software, because that's kind of boring, right? Why don't I just list these steps? They'll be helpful to you. So, 1, we measure the angle. I'll put horizontal angle. We have so many angles we're dealing with, it's helpful to inform you what angle I'm talking about. So measure the horizontal angle from back sight to edge of sun. 2, from the ephemeris, we have a semi-diameter at that particular time. Apply center, not center. Semi-diameter correction to calculate the horizontal angle from back sight to center of sun. Then 3, we would use the Greenwich hour angle and declination and the instrument latitude. Use shorthand there, the instrument latitude. Those are the 3 pieces of information we need to calculate the azimuth of our solar observation. Corrected to the center of the sun. And finally, calculate what we really want. Calculate azimuth of the instrument to the backside. And that is very, very, very high level, basic, in a nutshell version of a solar observation. The calculations are not that complex. They're actually really simple to automate. So you can build a spreadsheet or just write some C# code or some Python or even VBA for Excel to calculate, to reduce the calculations of a solar observation over and over and over again. It's kind of a fun little project. Might actually assign that one year, but I know we do it in another class, so I don't know. We'll see. Anyway, fun calculations. I think I'm going to stop it there, and next time I have a little bit to wrap up on moving from the concept of the celestial sphere to our use of time and the different kinds of time that we apply to celestial observations. So anyway, just a fun little conceptual lecture today, a little lighter than we've been doing. But I thought it'd be nice to take a little brain break, and the next lecture will be a bit of a brain break also, before we start getting into the concept of the ellipsoidal model of the Earth. Okay, so have a great day.